Hi everyone, welcome back to Lulumath. This video is on parent functions, and this is part 2 of 2 videos. In this video, we're going to talk about the parent functions of absolute value functions, reciprocal or rational functions, and exponential functions. Part 1 talked about linear, quadratic, and square root functions, so if you want a refresher on that, please make sure to check that video out at lulumath.com or the Lulumath YouTube channel. So background information you'll need is parent functions part 1 as well as domain and range. So just a reminder that in a family of functions, a parent function is the most basic function that keeps that family's characteristics. So the families of functions that we're going to be looking at are absolute value, reciprocal, and exponential. Let's take a look at the fourth parent function that we need to look at. 1, 2, and 3 are on the first video for parent functions. And here our parent function is f of x is equal to the absolute value of x. So let's get a general look at what this will look like. I'm going to go ahead and type in f of x is equal to, and right here is the absolute value key. So we'll click on that and we'll say the absolute value of x. And here is what our graph looks like. And just so that you know, you can also type in just ABS and then open up your bracket and then type in X, and it knows that that's the absolute value if you want to just use your keyboard. So this is what our graph looks like. And if you see, we have a y-intercept at 0, 0, we have an x-intercept at 0, 0, and we have a vertex at 0, 0 as well. So 0, 0 is really the main focal point of our graph. Aside from that, any points to the left and any points to the right will work for our chart or our table of values. So if you see, we have some points that I have shown here, -5, 5, -2, 2, 1, 1, 6, 6. These are just arbitrary random points that I have in the graph. But if you notice, they're all positive because when you take the absolute value of any number, no matter what number it is, it's always going to be a positive value. So in making my table of values, like we said, that 0, 0 is the focal point. So I'm going to put 0, 0 in the middle, and then I'm just going to go up and down by ones. And the absolute value of -3 is +3. The absolute value of -2 is +2. The absolute value of -1 is +1. The absolute value of +1 is +1, and so on and so forth. Then I will set up my graph. And as always, don't forget to number and label your axes. And I will go ahead and plot my points and connect my points as well. Now, unlike a parabola, we want straight lines. We do not want a gradual curve. And here we have f of x is equal to the absolute value of x. Now let's talk about the key features. So looking at our graph, we can see that our x-intercept is at 0, 0, our y-intercept is at 0, 0, and our vertex is also at 0, 0. Now these will change once we start to have transformations done to our graphs. Now let's talk about the domain. So the domain of our absolute value graph here, we have to think, what are the values of x that I can plug in here that will work or that won't work? Well, every single value of x I can take the absolute value of. The absolute value of x can go anywhere to the left, anywhere to the right. There is no limit. It's boundless. So that means that the domain is any real number. Or we could just say it goes from -infinity to +infinity. However, for the range, we know that our graph will not go below the x-axis. It has to be from 0 and above. So that tells us that our range is going to say y is an element of the reals such that y is greater than or equal to 0. Or we could also say f of x instead of y here. Or we could say from 0 to infinity with an open bracket on infinity because we'll never reach infinity, and a closed bracket on 0 because it can be equal to 0. Exactly like what happened with our quadratic parent graph, f of x equals x squared. Now, an important note right here is that no matter what types of transformations we do to our absolute value graph, the domain will always be all real numbers. So this is true for the entire family of absolute value functions, no matter what types of transformations we do to it. The range, however, depends on the transformations. because the transformations are going to change where this vertex is. So our lowest point will be somewhere else, and it might even flip or reflect the graph over, so making that vertex a maximum instead of a minimum. And we'll get into all that stuff when we look at transformations of graphs. But these are our key features of our absolute value parent graph. Okay, the next parent graph that we're going to look at is the reciprocal function, and this one is a tricky one, so pay really close attention to this one. The parent function is f of x is equal to 1 over x. Let's take a look at what this will look like using Desmos. So this is what our graph looks like using Desmos. This is called a hyperbola. So if we take a look at this graph, if you notice, as the x values get larger, the y values are getting smaller. So here we're at 1, 1. Now let's go to 3, for example. 3 is at 0.33 repeating. Look what happens as we get closer to 10. Our y value gets smaller, it's 0.1. Look what happens as we get closer to 20. Our y value keeps getting smaller and smaller. Let's move to the right a little bit and zoom in. Notice how the larger our x values are, the smaller our y values are becoming. Let's see what happens as we make our x values smaller. So as we get closer and closer to 0, if you notice, our y values are rapidly increasing. So if you see here, our x values are really small, but our y values are getting larger and larger. Look, when I go over here, we're already at 123. Now we're at 217 when the x value is 0.0046. And the same thing is true for our negative values. For really, really small negative values, our y values are getting farther and farther down into the negatives. But for large negative x values, our y values are getting closer and closer to 0. So why is this happening? Let's think about this for a second. If I were to take f of 4, for example, it would be 1 over 4, which is 0.25. So that gives us a coordinate of 4, 0.25. If x was 1/2, for example, then this would be 1 over 1/2. Well, 1 over 1/2 means 1 times. We do the reciprocal, and this is 1 over 2, which is 2. So when our x value is 1/2, our y value is 2. Well, what happens if I have 1 over 100? So this would be 1 over 100, which turns into 1 multiplied by 100, which is 100, which means that our coordinate would be 1/100th, which is tiny, 0.01, with 100 as our output. So essentially, all we're doing is we're just taking the reciprocal of our input. If our input was 4, our output was 1/4. If our input was 1/2, our output was 2 over 1. If our input was 1 over 100, our output was 100. This should say f of 100, sorry about that. If our input was positive, it was just 100, then our output would be 1 over 100, so it would be tiny. So as our inputs get smaller, our outputs get larger. As our inputs get larger, our outputs get smaller. So let's go ahead and make our table of values. So if x is -3, for example, our output would be -1/3. If x was -2, our output would be -1/2. If x is -1, then our output is -1. I want to get into some fractions as well. If our input is -1/2, our output would be -2. And if our input was -1/10, for example, then our output would be -10. Now, what happens when I get to 0? If I were to find f of 0, it would be 1 over 0, which is impossible. This is undefined. I cannot divide 1 by 0. And the reason why this is happening is because if you see right here, as we get closer and closer to 0, our y values are getting closer and closer to infinity. It's getting larger and larger and larger, but infinity isn't an actual number, so it's undefined. We can't say what you get when you divide 1 by 0. So here we're going to say undefined, and this is going to be really useful when we get to the point of finding our domain. For our positive values, I'm going to use these same values here, but positives. So I'll use 1/10, which means that our output would be 10. I'll use 1/2, giving us an output of 2. I'll use 1, giving us an output of 1. 2 gives us an output of 1/2. And 3 gives us an output of 1/3. And I'll go ahead and separate my table of values here so we can see a little bit more clearly what corresponds with what. Let's go ahead and set up our graph. Label your axes, X and Y. Now, when I number my axes, I'm actually going to go up by halves. So this will be 1, this will be 2, this will be 3. What gets really interesting is closer to the origin as opposed to large values of X. So I'm just going to go by halves here. And then for my Y values, I'll just still go by 1. And actually, I'm going to go here and I'm going to change my input here of -1/10 to -1/7 only because I just want to be able to see it fully on my graph the way I have it labeled. So I'll make this -1/7, but the reciprocal of -1/7 is -7. +1/7, the reciprocal of +1/7 is 7. So let's go ahead and graph out our points. So -3 is at -1/3. So we will put this point here. -2 is at -1/2. -1 is at -1. -1/2 is at -2, and then -1/7, which is closer to 0, is going to be at -7. And so my graph right here will end up looking like this. At 0, it's undefined, so I have nothing to place there. For 1/7, it's at 7. Then I have 1/2 is at 2, then 1 is at 1, 2 is at 1/2, and 3 is at 1/3. So this is what my parent graph will look like. Now let's talk about some key features. If you notice, our graph does not have an x-intercept and our graph does not have a y-intercept. Now this is true of the parent function, but if we do some transformations where we move the graph up or down, left or right, we will start to get some intercepts. But in the parent function, there are no intercepts. The domain is important. Remember, the domain consists of all the x values that work. Well, if I look at what we have here, the only x value that doesn't work, the only number that I cannot put in for x here is just 0. Any other value I can put in for x. So the way we write this is we say x is an element of the reals such that x is not equal to 0. Could be anything except for 0. Now, in interval notation, and I strongly suggest you check that video out to fully understand interval notation, but basically what's happening is it can work from -infinity to 0, but not including 0. This is a union symbol, so that's combined with 0. It starts working after we hit 0, all the way to infinity, but it does not include 0 and it does not include -infinity or +infinity. So this is what happens for our domain here. Let's go back to Desmos to talk about the range. Now, if you notice, for large values of x, it gets closer and closer to 0, but our graph does not touch 0. Let's fix our zoom on our graph so we can see what's happening for really large values of x. So we'll go from -1000 all the way to +1000, and our corresponding y values are getting really, really small. So I'm going to go from -0.1 all the way to +0.1. And if you see on our graph, it looks like it's going to touch the y-axis, but it's not. It's going to get really, really close, but it just doesn't quite touch that y-axis. See, when we zoom in right here, it's not touching that y-axis. Let's go even smaller. Let's do -10,000. And +10,000. So if you see here, again, it looks like it's going to touch the x-axis, but it doesn't, which means that y will never be equal to 0. And thinking about it logically, there's no way that I can do 1 divided by some number and get 0. There's just no possible way I can do it. So for our range, we are going to say something very similar. Y is an element of the reals, or f of x is an element of the reals, such that y, or f of x, is not equal to 0. Or we could say it goes from -infinity to 0, does not touch 0, and then it starts again at 0 and goes all the way to infinity. And these are our key features of our reciprocal function. Now, really quickly, this line, y equals 0, and this line, x equals 0, our green graph will never ever touch these lines. So these lines right here are something called asymptotes, which means that our graph will try to approach these lines, but they'll never be able to touch them. Now our last parent function is an exponential function, and this has an asterisk on it because exponential functions actually have multiple parent functions. It just depends on what the base is. So the parent function for our exponential is going to be f of x equals b to the power of x, where b can be any base. So for the purposes of this video, we're going to use 2 as our base. So we'll try 2 to the power of x. Let's go ahead into Desmos and take a look at what it's going to look like. So this is our graph. F of x is equal to 2 to the power of x. And if you notice, we have a y-intercept right here at 0, 1. And our graph will rapidly increase as the x values get larger. And as the x values get smaller, our graph will decrease and get closer and closer to 0. And although this says 0 in Desmos, when I zoom in on it, it in fact is not 0. It's just rounding it down to 0. It will never, ever, ever touch 0. So here's a case of another asymptote. Now, because it never touches 0, it means that we only have a y-intercept and we don't have an x-intercept. Let's go ahead and make our table of values. So let's just go from -3 all the way to +3. When I raise 2 to the power of -3, when I have an input of -3, that means I have to do 1 over 2 to the power of 3. And if you need an explanation on that, there's a video on negative exponents. So 2 to the power of 3 is 8. So I end up getting 1/8. To find f of -2, it would be 2 to the power of -2, which is 1 over 2 squared, which is 1 over 4. F of -1 would be 1 over 2. F of 0, anything to the power of 0 will always be 1. And that is why our y-intercept is at 0, 1. A common mistake people will make is they'll think it'll go to 0, 0, but that means that our graph here will increase, get really close to 1, and then it'll jump down to 0 and then go back up, which doesn't make sense. And then when our exponent is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, and 2 to the power of 3 is 8. Let's go ahead and set up our axes. And because our graph is all positive, I'm going to put my x-axis lower because I don't really care about negative values. Number and label your axes. And our first point that we see here is -3, 1/8. So I'm going to go to -3 and about 1/8 of the way up. Then I've got -2, 1/4. So I'll go 1/4 of the way up. -1, 1/2. 0, 1, 1, 2. And I'll just keep going with my points. So this is what my exponential graph will look like. So let's get our key features down. So we know that there is no x-intercept. It tries really hard to get close to the x-axis, but it never touches the x-axis. So if you remember in our last example, that means that our x-axis here ends up being an asymptote. There's an asymptote at y equals 0. For our y-intercept, we know that it intersects at the y-axis at 0, 1. So our y-intercept is 0, 1. Now let's talk about our domain. X could be any value. I can plug in x here, 2 to the power of x. I can raise 2 to any exponent I want. And even if my base wasn't 2, if my base was anything, I could raise it to any exponent I want. There is no limit to the left side and there is no limit to the right side. So therefore, my domain is x is an element of the reals. Or we could just say from -infinity to +infinity. All x values will work. Our range, however, is it will only work above this asymptote that we have here. So that means that our range will be y is an element of the reals, or f of x is an element of the reals, such that y is greater than 0, not greater than or equal to 0, because it will never touch 0. So this is different than our absolute value graph and our quadratic graphs. Or we could just say from 0 to infinity as follows. And these are our key features of our exponential graph. Now, one quick note that I would like to tell you is that this is true for f of x equals b to the power of x. So no matter what our base is, we will always have these key features. Now, once we start to do some transformations though, our x-intercept our y-intercept and our range could change, but our domain will always be x as an element of the reals, no matter what. And that's it for this video. Thank you for watching. If you have any questions, let us know in the comments below or at lulumath.com, where you can also find blank or completed notes for this video. If you found this video to be useful, please make sure to share with others and subscribe. Thank you, and we'll catch you next time. Bye.